Okay, today we're going to talk about Chapter 1, Section 5A, the first part of it, talking about functions and logarithms. First thing that we need to know before we get into logarithms is to understand what a one-to-one function is. A function f of x is said to be one-to-one on a domain D if f of a can never equal f of b, whenever a equals b. A nice way to remember this is in order for a function to be a one-to-one function, not only must it pass the vertical line test, but it also must pass the horizontal line test. So every x can only correspond to one y, but every y can only correspond to one x as well. Another good way to tell if a function is one-to-one or not is a one-to-one function is always increasing or always decreasing. It cannot change from increasing to decreasing, or vice versa. As soon as a curve turns, it will no longer pass the horizontal line test, and it can no longer be a one-to-one function. Even though we have functions like y equals x squared, which is not one-to-one, we can often limit a function that is not one-to-one to a one-to-one portion, and then work with that particular part of the function. In other words, y equals x squared is not one-to-one, but if we say y equals x squared, comma, when x is greater than or equal to 0, then that half of the parabola is one-to-one, and we can find its inverse function then. When we're writing an inverse function as a function of x, notice that this is the notation for an inverse, f to the negative first power. It doesn't mean 1 over f of x. Okay? What we want to do, I always do these the other way around. I do step 2 first. So I will interchange x and y, and then I will resolve for y. Okay? And the resulting formula will be the inverse function. So that's the way that we'll do it in class. We'll switch x and y and then resolve for y. Okay? Definition of some logarithms. Base A logarithm function. The base A logarithm function y equals log base A of x is the inverse of the base A exponential function y equals a raised to the x. So it's really important to know that logarithmic functions are the inverses of exponential functions. That's why we need to have logarithms, so that we can find the inverse of an exponential. When we talk about a logarithm, I think it's important for you to know that logarithm means exponent. In other words, it means find the exponent. If you're given a base, find what the exponent has to be in order to give you a particular number. And that's what we're doing when we find logarithms. We're finding out what does the exponent have to be in order to give us a particular number if we are given a specific base. Here's some properties of logarithms that you need to be aware of. Log base A of 1 equals 0. It doesn't matter what the base is. It could be a natural log of 1. Any logarithm of 1 is always 0, because logarithm means the base raised to what power has to equal 1. So we know the exponent has to be 0 in order to get 1. Therefore, the log of 1 is always 0. Similarly, the log base A of A is always 1. Again, this means if the base is A, what do we have to raise it to in order to get A? A to the first power equals A. That's why log base A of A equals 1. The third property here is base A raised to a log base A of x equals x. A log base A of x equals x. Okay? You know that one. And also log base A of a to the x equals x. If we think of this last one right here, makes sense. It says the base is a raised to what will give us a to the x. It has to be raised to the x. Okay? So those are 4 properties for logarithms we definitely need to know. Other properties of logarithms that we need to be aware of and use quite frequently is the product rule. It says if you take the logarithm of a product, you can take the log base A of the first factor plus log base A of the second factor. It's the product rule for logarithms. The quotient rule for logarithms says if you take the log base A of a quotient, it's the log base A of the numerator minus log base A of the denominator. The power rule for logarithms says if you have a log base A of x raised to the y can drop down and become the coefficient of the logarithm. and therefore it's y log base A of x. Change of base formula. This will be very important. We'll use this constantly throughout the year. We hardly ever look at anything in calculus as a logarithm. We always change it to a natural log, which is a form of a logarithm, but we will almost always use natural log. So if we have log base A of x, it is the natural log of the argument over the natural log of the base. That's how you say it. The x part is called the argument. Natural log of the argument or the natural log of the base. Okay? Determine whether the following function has an inverse function. In many cases, you almost need to graph it to figure out if it's one-to-one. Sometimes you can figure it out just by knowing if it's an odd or even function, that type of thing. If you look at this particular situation right here, this is a one-to-one. This will be yes. It has a vertical asymptote at x equals 2, and it will end up having a horizontal asymptote as well. If you get a common denominator, it has a horizontal asymptote, something like at -1. But every x only goes to one y, and every y only goes to one x. If we want, we can type it in. It's 3 over x minus 2 minus 1. So if we type it in, y equals 3 divided by parentheses x minus 2 minus 2, close the parentheses, and subtract 1. And if we graph this, I'll go zoom 6 for zoom standard, we can see it passes both the horizontal and the vertical line test. It continues, if we look here, it continues to get closer and closer and closer to the horizontal asymptote, but every x value has only one corresponding y value. It is 1-to-1. We come back to this one, x cubed minus 4x plus 6. Cubic functions are hard. Sometimes they're 1-to-1, sometimes they're not. If they turn over, they're not 1-to-1. So let's go back and look at x cubed minus 4x plus 6. X, math 3 for x cubed. I think that's the best way to do it. Minus 4x plus 6. If we graph this, I'll go zoom 6. Here it comes. We see that it turns. It does not pass the horizontal line test. We could draw a horizontal line right here and cut it in more than one spot. Therefore, this is not 1-to-1. Okay, so this is no. The natural log of x squared. This could be kind of challenging. When we take a look at it, if we type it in just like it looks, the natural log of x squared, we're going to get y equals the natural log of x, natural log of x exactly why I like to use the calculator in class, because these buttons. Zoom 6. If you take a look, it comes here, and then it comes back up. We do get a vertical asymptote right here. You can see it a bit better if we don't thicken this. If I go back, just regular graph here. You can hit graph. It's not quite as thick. You can see that it goes down more. But it is a vertical asymptote at x equals 0. It does not pass the horizontal line test, however. It is not 1-to-1. So this is no. On x squared minus 4x, this is a parabola that opens upward. You should be able to tell right away that this is no. We can check it, however, in the calculator. X squared minus 4x. And we see it's a parabola. It opens upward. It does not pass the horizontal line test for 1-to-1 functions. X cubed plus 4x, again, this one can be kind of tough. It actually, this one should turn out to be a 1-to-1 function because it only has one x-intercept, and that x-intercept is 0, and it's a cross, not a touch. So this is going to turn out to be yes. But let's take a look just to make sure. X cubed plus 4x. Y equals x math 3, or x cubed, plus 4x. One thing that you will notice with these is that sometimes the functions can look as though they're pretty easy to switch x and y and solve, but on one like this, it's not so easy. Being able to switch for x and y can be a problem sometimes. It's not always the easiest thing to do. Okay, x cubed plus 4x. Let's go zoom 6. Here's the cubic. It does not turn over, so it is always increasing. It is a one-to-one function. This is yes. And likewise, this exponential functions. Most exponential functions are one-to-one. That's why we have logarithmic functions, to undo the one-to-one function. 3 raised to the 2 minus x. I'm going to clear this out. I'm going to clear this out. I'm going to go 3 raised to the 2 minus x. Cursor to the right to get back down here. We're going to go zoom 6. Okay. And we see it's a one-to-one function. It has a horizontal asymptote at 0. It does continue to grow this way, but it does pass the one-to-one function test, both the horizontal and the vertical line test. So this is one-to-one. Okay? All right, this is where a lot of the assignment will be centered around these types of problems. They get pretty long. I'm going to try to do at least some of the shorter ones here. I may have to do some of the longer ones in class because there just isn't enough room on the smartboard, especially when we do the verification. Because here's how it works, and I will ask you to verify. First, it says find the inverse of the function. Very first thing we're going to do is write y equals 2x plus 3. We're going to switch the x and the y, and we're going to resolve for y. If we resolve for y, we're going to subtract the 3 over, and we're going to divide by 2. That's going to be the inverse function. You can write it, it's f negative 1 of x. You can either write it x minus 3 all over 2 if you want. There's nothing wrong with that. If you want to write it more in a standard linear format, we would write 1/2 x minus 3/2. Now it's a nice slope-intercept form. But either way is fine. But the real work comes with cranking out the composites. Yes, if you did this correctly, everything should work out fine. So it's a nice way to check. And sometimes students, they find this quite cumbersome, and I agree. You got to crank these out even though you know that you found the inverse correctly. But the whole idea is that you are supposed to show that when you do these composites, you will get x every single time. So we're going to first of all show f of f negative 1 of x. Take x, plug it into the inverse function. When you plug x into the inverse function, this comes out. And now you have to take that and plug it into the f function. When that comes into the f function says take 2 times whatever comes in and add 3 to it. So it's 2 times whatever comes in. This is coming in. Add 3 to it. Distribute. We're going to get the 2's to cancel, x minus 3 plus 3, which is x. So it works the first way. You have to do both ways. So now you have to do the second composite, which is f negative 1 of f of x. Take x. If we put everything through this way, the inverse of f of x, take x, plug it into the f function, and 2x plus 3 gets kicked out. Now take the 2x plus 3 and plug it into the inverse function, which says take 1/2 of whatever's coming in, and then subtract 3/2. If we distribute, the 2's cancel, we get x plus 3/2 minus 3/2, which also gives us x. There it is. That's the verification. On the test, quiz, homeworks, I expect you to make this summary statement. Since f of -1 of x equals f -1 of f of x equals x, the functions are inverses. Okay? There's that step. Let's do another one. Same idea, doing it with a cubic function. First of all, to find the inverse, here's y equals x cubed minus 1. Switch x and y and resolve for y. Take the cube root. There it is. Y equals the cube root of x plus 1. So the inverse function is the cube root of x plus 1. Okay? Now to crank out the composites, doing the same thing. F -1 of f of x. It doesn't matter which one you do first. Take x, plug it into the f function. X cubed minus 1 comes out. Now you have to plug this into the inverse function. The inverse function says take whatever comes in, add 1 to it, and take the cube root of it. Here, -1 and +1 will cancel, and it's the cube root of x cubed, which equals x. If you don't get x back out, you either found the inverse incorrectly or you cranked out the composite incorrectly. The composite here, f of f -1 of x, take x, plug it into the inverse function, which is the cube root of x plus 1. Now, plug that into the f function. The f function says take whatever comes in, cube it, and subtract 1, which is x plus 1 minus 1. Cancel. I can always tell whether you did it correctly or not by checking the last steps. Notice here the last step was the cube root of x cubed in order to get x, where here in green the last step was x plus 1 minus 1. If you try to fake it, it's easy for me to see. It is easy for me to see. That's x. And again, we make a summary statement. It's the same thing every time. Since f of f -1 of x equals f -1 of f of x equals x, the functions are inverses. Okay? Questions on that? That's how these will always work. Okay? All right. We're going to skip this one. It becomes a bit of a problem because of these negative signs. There is a few like this in the homework. We'll talk about this somewhat in class, but I don't want to confuse you when you're watching this one online. So we're going to just go to the next one for this particular situation. Okay? This one here isn't too bad because it's the positive part of this. If you look at 1 over x squared, it is not a one-to-one function. But if we limit it to the right half of it, it is 1-to-1, and that's what's going on here. We're saying this is only true when x is greater than 0. And since it's only true when x is greater than 0, we can still find the inverse. Switch x and y. Resolve for y. Y squared times x will equal 1. divide, take the square root. Now when you take the square root, you need to consider the plus or minus square root of 1 over x. The square root of 1 is 1, and square root of x is the square root of x, but you need to consider, is it going to be the positive or the negative? Well, if only positive values are coming in for x, then only positive values are coming out for y. It's not going to be the negative values for y, it's going to be the positive values for y. So it is the square root, or it's 1 over the square root of x. You do not have to rationalize algebraic expressions. We can leave it just like this. Okay? This will be fine. So our inverse function, to write it in inverse format, is f negative 1 of x equals 1 over the square root of x. Cranking out the composite. F negative 1 of f of x. Take x, plug it in to the f function, and get 1 over x squared. Now take that and plug it into the inverse function. The inverse function says take 1 over the square root of whatever comes in. The square root of 1 is 1. Square root of x squared is x. Flip is x. Let's crank it out in the opposite direction. F negative 1 of f of x. Take x, plug it into the f function. This comes out. Now crank that into the inverse. When we crank that into the inverse function, that's the direction I just did it. Let's go back, do it the other direction. Okay? So f of f negative 1 of x. Take x, plug it into the inverse function. We get 1 over the square root of x out. That now is the input into our f function, which says take 1 over whatever comes in squared. Again, it's 1 over x. Flip, again, is x. And then we write our summary statement. Since f of f negative 1 of x equals f negative 1 of f of x equals x, the functions are inverses. And we're going to write this every time. If you don't, you're going to miss a point on tests and quizzes. And I'm going to look on your homework to make sure it's there. Want it every single time. Okay, this is probably the hardest one when we're dealing with these rational situations. Just because they're a little bit more involved. Just kind of taking a look. We'll crank this one out real quickly though. At least getting the inverse function part of this. We did one like this today in class. If we say y equals 2x plus 1 over x plus 3, if we switch x and y, here's what we get. A lot of students struggle then when I say resolve this thing for y. It shouldn't be that tough. Multiply the y plus 3 up. A lot of it, and the reason why I say I'm not trying to be condescending when I say it shouldn't be that tough, I'm just trying to be honest in terms of it flows just in a natural progression. For lack of anything better to do, we cross multiply and get everything on the same level. I mean, there's nothing else that we can do. That step right there is kind of let's at least make everything on the same level. Now, as we look at this, what are we going to do? We got parentheses, so let's at least distribute the x. So we get to this point, and we say to ourselves, we're trying to resolve for y. Well, if we're trying to resolve for y, let's get all the y's on one side. So let's subtract the 2y over here. Let's subtract the 3x over here. So any term involving a y comes to this side. Any term not involving a y goes to the other side. And then we can factor the y out front. So these are all pretty generic algebraic steps that just kind of flow. There's really not much else you can do but to do each step as you progress. So if you just follow through with really the best move, you're going to find out that the inverse function is 1 minus 3x over x minus 2. Now students don't like the rational ones because they do involve a lot more detail when you go to crank out the composites. And here are the composites. If we're going to go f of f negative 1 of x, we'll go this direction first, although it doesn't matter. The inverse function, again, is 1 minus 3x over x minus 2. 1 minus 3x over x minus 2. That's the inverse. Now, it's got to go through the f function. The f function's defined right here. It says whatever comes in, take 2 times whatever comes in, add 1, over whatever comes in, plus 3. So, we're taking 2 times whatever comes in, which is this, and add 1 all over whatever comes in, plus 3. Okay? That's what this function defines for us to do. Okay? Now, there are a number of different ways that you can simplify this complex fraction. You can make the top all one fraction, make the bottom all one fraction, and flip. We talked about that today in class. But it is much easier if you simply multiply the numerator and the denominator by the common denominator of x minus 2. Because if we distribute it, the x minus 2 will cancel. We're just going to get a 2 times a 1 minus 3x. And here we just get a 1 times an x minus 2. Here, if we distribute, the x minus 2's cancel. We get a 1 minus 3x, and we get a 3 times an x minus 2. If we distribute the top, we're going to get a 2 minus 6x plus x minus 2. If we distribute the bottom, 1 minus 3x plus 3x minus 6. And look what ends up happening on top. These cancel, and we get a negative 5x. Here, these cancel, and we get a negative 5. The negative 5 cancels, and voila, it's x. It's going to be x every time. It's just a matter of you making it work out. It's going to be x every time. The bad part is that's a lot of work, and now we still need to crank it out in the other direction. So now we need to say, we did f of f inverse, now we need to say f inverse of f of x. Take x, plug it into the original function, you get out a 2x plus 1 over x plus 3. Now this is going into the inverse function. The inverse function says take 1 minus 3 times whatever comes in, all over whatever comes in, minus 2. So I'm going to take 1 minus 3 times whatever comes in, all over whatever comes in, subtract 2. We're going to do the same thing that we did in the last problem. We're going to multiply both top and bottom of this by the denominator of x plus 3. You have to distribute it to both pieces. And look how well this works out. X plus 3 times 1 is just an x plus 3. If we take x plus 3 times this, the x plus 3 cancels. We get a minus 3 times 2x plus 1. That's what we get right there. If you distribute, the x plus 3 cancels. You get a 2x plus 1. Distribute, you get a minus 2 times x plus 3. So on top, we get x plus 3 minus 6x minus 3. Down here, we get a 2x plus 1 minus 4, or minus 2x minus 6. Again, look what happens. The 3's cancel. Here, the 2x's cancel. So we are going to get on top negative 5x, on the bottom a negative 5. And those cancel to leave an x. Voila, it works. It should work every time if you do it correctly. We make a summary statement, f of f negative 1 of x equals f negative 1 of f of x equals x, and we want to say since the functions are inverses. I will do it every time in class. You need to make sure you do it in your homework. Okay? It's a lot of writing, I know. Try to go back up to see it. It's a lot of work on this, but it is great practice for that extra algebraic type work that we need to be able to do. What students have really struggled with a little bit the last couple of years are the heavy algebraically intensive problems. We've got to make sure that our algebra is solid. When we're doing these problems right here, use parametric mode to graph these, the function, and then its inverse. Here's how they want you to do it. Number one, I do think you should be able to find the inverse of any of these functions. If this is y equals e to the x, switch x and y, resolve for y by taking the natural log, and that's why we know that the inverse of the e to the x is the natural log of x. There it is. Same here. If I want to find the inverse, y equals 2 raised to the negative y, switch x and y, resolve for y. Take the natural log of both sides. Watch what happens here. Now the negative y drops down. Our properties for logarithm says that it will. And now to get y by itself, we divide by a negative natural log of 2. So it's a negative natural log of x over the natural log of 2 will equal y. That will be our inverse function. Negative natural log of x over the natural log of 2. So all of these inverses you should be able to find by hand. Here, if y equals the inverse sine of x, switch x and y. To resolve for this just says then that the sine of x equals y, and that's why we get y equals the sine of x. Okay? And so the inverse function here is simply the sine of x. But the bottom line is they really want you to just show it in your calculator. So if I have e to the x, the whole idea behind this, and then they want you to graph y equals x. I'll do one of these, and then I'm going to run out of time here. So I'll just do one so that you can see how they want you to type it in parametric mode. So I'm going to change my mode. I'm going to go over to parametric. I'm going to hit enter. Second quit, I'm going to go y equals. Okay? And here's all they want you to do for this. For the first equation to graph it, a normal function, I just make x equal to t, and I'm going to go second e raised to the t. Again, the buttons here. Second e raised to the t. Wrong spot. Second e raised to the t. Cursor to the right. All I'm going to do with the second equation then is switch the x and the y coordinates, because that's what we do with inverse functions. So I'm going to make the x coordinate be second e raised to the t. And I'm going to make the y coordinate equal t. To graph the line y equals x, I just have to make the x coordinate t and the y coordinate t. I do have to set my window. I don't want to start at 0. I need to make sure it goes off the screen here. So maybe I'll go from negative 10 to positive 10, and I will step 0.1. So let's graph this and see what happens. Here comes the exponential function. Here comes its inverse function. And then here equals the y equals x. And you can see that they are mirror images about the line y equals x. That's how they want you to do these problems. And then you'll produce this graph on your paper. So if I were to look at something like 2 raised to the negative x, again, I'll do this last one for you because then I'm going to be done. 2 raised to the negative x. So y equals, I'll make that t. This is going to be 2 raised to the negative t. I'm going to go enter. Then I'm going to go 2 raised to the negative t. The rest of it I'm going to leave the same. This is t. These two are t. Hit graph. If I go from negative 10 to 10, it should be fine. Here's this exponential function. Here's its inverse. And here's the line, y equals x. And they are mirror images about themselves. Okay? The last one, I guess I'll do it while I'm here, and then we'll talk about it in more detail in class. But if I go back, it's the inverse sine of x. Okay? So if I go back to my smart view, it's the inverse sine of x this time. So I'm going to go, that's t. This is the inverse sine of t. T. This is inverse sine of t. I'm going to close it. Okay, now I got to delete this stuff out. Should have just cleared it first. There it is. Okay, here, I'm going to clear it. I'm going to type in inverse sine of t. Inverse sine of t. I'm going to close it. The rest of it all stays the same because it's t, t, all the way down. Here we go. Graph. Here comes the inverse sine function. It's very small. Okay? It stops. Inverse sine function actually stops. We'll talk about it in more detail. If you want, you can go zoom 7 for zoom trig. See if that gives you a little bit better picture of it. But that's what it's going to look like. So you produce those graphs on your paper. Okay? That's it for 1.5a. I know we skipped the one. We may talk about a little bit more in class. When you come back to the lesson, here is the assignment. 1 through 6, 8 through 32 even. Work on them the best you can. If you're looking at it tonight, just please make sure you take a look at it and get as much done as you can. All right? See you in class.